All right, let's start with physics. Initially, we were planning for George's lecture first. He's going to talk, give us introduction to QCD, but he told us that he can do the second lecture, not the first. And so you have to suffer now me giving the first lecture. I'm going to tell you about the 3D structure of the nucleon in the momentum space and the electron ion collider. And I've taught many schools, and each time I teach a school, I think, what's in it? It's summer, it's my vacation time now, summer for you as well. So, and then it's easy to figure out what's in it for me because I like teaching and I like talking. Here I am. It's very easy. Now the question is, what's in it for you guys? And I looked up because the names here, and then I realized that we have a group composed of theorists, experimentalists. For instance, who identify yourself as an experimentalist? Are there experimentalists here in the room? Very shy experimentalists. But I see the hands. What about theorists? Are there theorists here? Oh, wow, we have a lot of theorists this time. Oh, excellent. Okay. I myself, I'm a phenologist. I'm doing phenology of 3D structure of the nucleon space. And when I was thinking about the lectures, I decided for this very school, let me use everything that the center provides us. Well, the center provides us with technology. Get our Zoom here, we have the screen here, so I can preach, of course, to you all the time, but it gives also this thing, which I personally love very much. And it's not very convenient, unfortunately, for students, and the person is writing there. But I mitigated that. I actually put all my notes already on the school page, so you can follow me there. Okay. So what I'm going to be doing, I will be using both this screen here and the blackboard. The blackboard will slow me down. So I can speak faster than I write. Okay. Now I'll try to cater for theorists. So I'll give you some knowledge of calculations that I do, or some techniques on the blackboard, how I do those calculations. I'll give some knowledge to experimentalists. I'll give you today already a Google Colab notebook where you can open up and perform a calculation prediction, say, for your kinematics for a particular asymmetry. Okay, so we'll look at it today. Okay. And I wanted to divide everything in sort of questions. And so these questions will be the following. What is the 3D structure? Okay, and then once we know what the 3D structure, I would like us to ask a question. Well, why to be excited about that? Why should you care about 3D structure? And then, of course, why the electron ion collider? Well, the last question is probably the easiest because, well, we know where we are going to study the 3D structure. We are going to study the electron ion collider. The question is why? What is the advantage of this facility? But I will start with the first one, and this one, the first one, what? What is the 3D structure? Here are my lectures, lecture number 1, lecture number 2, the plan. And let's see how much can we go through. Lecture number 1, I'll talk about structure of the nucleon. I'll introduce the so-called transverse momentum dependent distributions, TMDs. That's what I study and like. I'll tell you about semi-inclusive deep inelastic scattering, CDS. That's the process that the electron ion collider we'll be using to study transfer momentum distributions. And I'll show you calculations of CD structured functions in Google Cloud. Okay. Lecture number 2, I'll go a little bit deeper in the theory. And so I'll introduce the solution of TMD evolution equations. We'll solve them together on the board, and we will derive the famous Collins-Sofer-Storm summation formula okay, for the cross sections and for the distributions. Lecture number 3, it's not mine. It's going to be given by Giuseppe Bozzi, but it will be dedicated to TMDs. He'll tell us about phenomenology of unpolarized TMDs. Basically, my main occupation is that. Well, I'm giving this lecture now in view of the first one, so let me not just well immediately into nitty-gritties of TMDs or whatever things we will be studying. Let me first introduce the material that I'll be using. The material first and foremost is this TMD handbook. That's the thing that we were writing for 5 years in TMD collaboration, sponsored by Department of Energy. That was our final project, a textbook of TMDs. So you're welcome to download this, and I base my lecture on that. Everything that I'll tell you these 2 days will be located on the Indico, and will be also located on GitHub, cfns.school. So you're welcome to clone this repository files, get files from there. Okay, so let's not go into the TMD table yet. There you go. So the question is, we would like to study, say, the proton. Okay? I'd like to study the properties of this proton in terms of partons. And what question is, what is the language that we're choosing for that? Well, of course, we are going to use the language of quantum mechanics. After all, it's a microscopic object, base laws of quantum mechanics. And then we talk about quantum mechanics, if you like, it's a separation of all our world in 2 pieces. Okay, one piece is a system that we study. That's our proton, and it's a microscopic thing. And the other piece is a big one. This one is a system. This one is big one, macroscopic one, that is classical laws. So okay. So once we do this separation, well, even about the detector, we can talk about the system and the language of quantum mechanics. You know that the system will be described by a wave function. Wave function is an object, so it's a continuous object, very wavy thing, you know? And it would evolve according to Schrödinger equation, no discontinuities, all like that. We will talk about this size, which is our wave function, which describes the system. We'd like to actually know something about the system. And then we start asking a question. Asking a question is this detector. Once we use the detector, then instead of our move continuous wave function, suddenly we're introduced Born rules, probabilities. Now we are talking about, once we use this one, about probabilities, squares of the other value of the wave function, about numbers. Well, this thing, this real and imaginary part, of course, as we know. At some point, once we detect, have these squares. That is important. Compared to classical systems such as detector, knowledge that we have about microscopic system is around the half. Okay, so we can know about the position, but we can know it, but cannot know about the momentum. Vice versa, the underlying Schrödinger, the uncertainty. Now, when we talk now about our plot, and that's what we're going to be studying, even if you like, quantum mechanics is not quite enough. Well, because we know that there are partners there, we learn that there are partners there, the number of constituents in our system is not fixed. Therefore, we have to change our language once again. So now we'll say, okay, so we will employ the language of quantum field theory. So we forfeit our a function. We can still define it, but what we'll do is that we'll say, okay, let's promote our knowledge to operators, field operators size. I'll use actually the same letters, so I'll not say that. That's an operator size. And this operator will act on objects which we call state vectors. And after Dirac, we use these notations for those state vectors. State vectors live in very peculiar state. Very difficult to trace into our 3 or 4 dimensional space, infinite dimensional space. So we have this state vectors. And now, of course, again, we have a detector which performs the measurements. Okay? So now let us start first drawing some pictures. How do we do measurements? We'll collide particles, well, experiments collide particles. In particular, this is what I'm going to be concentrating on. Suppose we have leptons colliding with protons, collides with proton, and we detect lepton final state, and its energy is equal to mc squared. The proton can be destroyed, so we produce what particles say in the final state. Okay, so this is what the electron ion collider is going to be doing. Accelerating leptons, electrons colliding with the targets, say suppose hydrogen targets in the nucleus, producing a lot of particles affecting the final state. This will be the underlying process that we're studying. So this is what is happening in terms of how these detectors work. Okay, so that's the past. And it was there, particles are produced, detected by detector. Okay, so this is what half of you, half of you experimentalists are doing, measuring those. Don't be mistaken, that's not what is happening in the head of the other half of all students or theorists. They're not thinking directly about this. What they are thinking, of course, about squares. Because once we do this, we square things. Okay. So when we talk about squares, we say, okay, we go, so we need to square all this. So this is how it would look like. This is what is in the head of the theorist. That's the amplitude. I multiply the amplitude by its conjugate, and I'm going into this. So now a theorist would start thinking hard about that. And he or she will say, okay, let's do certain manipulations with this object. It's a square. Let me introduce a unity operator, the integral of the phase space of my states which I don't observe, so x here. So x will be a unity operator. Okay, I'll apply the conservation of probabilities, and I'll get into the optical theorem to describe my cross sections. So this would look something like this. Okay, so lepton, 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 prime, P. So this is the amplitude we were studying. We squared this, did certain manipulations, came to this thing, which is definitely not what experimentalists are studying, but what theorists would derive one. Okay, and in particular case here we would say, okay, that's the amplitude. We'll take this dashed line. Dashed line is the summation of all the unobserved states here, which is what we call here is inclusive reaction, produce many particles. Well, here, what this means is imaginary part. So it's the imaginary part of this amplitude, which is good, perfect, because I wanted to get some numbers. Okay, I squared this thing. Where's the numbers? Okay. Amplitude is not a number. The amplitude can have real or imaginary parts. Therefore, I trace to the imaginary parts. This amplitude, which is a number. Okay, so I'm back to my Born rules. Okay, so now we came from here to there, and we start doing other steps. Well, first of all, we say, oh, right, so I know what is happening here. That's an electromagnetic current. The usual approximation which we take is a one photon exchange. Can be more. Usually one we do as a one photon exchange. We say, well, let me now do this. Okay, so my lepton emits a virtual photon. This virtual photon goes into my amplitude. Let's get from that amplitude, assuming that there is only one photon exchange. Well, 1 over 137 gives me a good probability that I get one photon exchange with ice. Now, what's important here is that now this upper part of the diagram here will contain information about electromagnetic interactions. While this bottom part of the diagram will contain information about things that we study here. So what we'll try to do is that we'll try to write this in terms of what is known as leptonic tensor of L mu. And because here we have coupling mu here, so L mu, we need still a number, of course, and then we'll multiply it by W mu, and L mu will be so-called leptonic tensor, and W mu will be our hadronic tensor. So at this point, what's important is it's this. Okay. So why it's important? Well, we have say L prime, okay, and momentum Q here. So Q is defined as say the difference between L and prime, and we just can square it. For instance, L minus L prime squared. It's a negative quantity. This particle is virtual one. So minus this is equal to capital Q squared, a big number. So one can show that this Q, the virtuality of the photon, plays an important role. It is the resolution power of this photon in the transverse plane of the nucleon. So if we imagine that our nucleon is a big, like one Fermi object. Okay. This is bigger the Q squared. The smaller portion of this we are testing with our virtual photons. Okay, and this virtual photon then will resolve particle nature of partons inside of our proton. Okay, I'm going very fast here, not paying much attention. Yeah, but just get the idea. Okay. So this photon here will resolve something inside of our object because we know the proton is composite object. We learned about this after years of experimentation, and you'll see details in many lectures here. So now from this diagram here, we will go to this particular diagram. Feel our object that we study. So it's our proton here. There. Now proton interacts with the quark. Okay. There's still imaginary part of this diagram. And quark goes through the pad, say this, and that's a famous Handback diagram. So, is there anybody who hasn't seen this diagram before? Okay. Everybody. Okay, so in the questions that I'll ask for our evening discussion, I would like you to actually motivate this diagram. I'll not do it for you. So what's important here in scattering is happening. So I told you that I was doing the square of the amplitude. And now the square of the amplitude here is my part here, and here is my part. And I'm drawing this diagram and saying it's the same work. It doesn't have to be. The question is why it's the same work that participates here. So this thing becomes a jet and goes through the detector. We can either detect or not detect. So we will talk about this in the evening. Think about this. If you don't know the motivation, try to figure out what you would do in order to motivate this particular thing. So now what's important here, of course, is that what we have done in this case is that we separated all our leptonic part here. The leptonic part now is interacting with quark. So that's the elementary interaction of the lepton and the quarks is proportional to what we call sigma zero, scattering quark. While what's here in this diagram is actually some non-perturbative knowledge of what is happening inside of the proton and how it's going to work. And it's a linear approximation would be just a function which parameterizes the fraction of the momentum R'd by the quark. And once you do, say, this cut diagram here, you figure out that there is a particular delta function of x minus q squared divided by 2 p dot q happens through here. That fixes this parameter x, which can be from minus infinity to plus infinity, to what is known as x Bjorken, q squared divided by 2 p dot q. This parameter is x Bjorken. Okay. It is experimentally measured parameter. It depends just on the experimental conditions. While this thing is something that sits in this matrix element, and a priori we don't know what is happening there. It can be x, can be anything. Now we are bound by x, which is actually x Bjorken. That's how, once we do this sort of scattering, and what I'm talking here is so-called deep elastic. But we are actually studying work with a particular momentum fraction, x. Okay. So now, when we do these approximations, we have to do a lot of approximations. What I draw here is just a Prokudin model. So there is no QCD here. There are no gluons at all. It's a Prokudin model. We have to, of course, make sure that we address everything with gluons and prove that the same picture works with QCD. And so the separation of this from that would be called factorization theory. That's what theorists would spend a lot of time proving. Factorization on its own is a controllable approximation that allows you to separate different scales. So you separate short-term interaction, short-time interaction, work with the long matrix elements works inside of the nucleus. So now let's talk about some names. So when we do this approximation, we approximate this quark being collinear to the proton, has basically only one momentum along the motion of the proton. It's parameterized by this x. X is just one number. That's why we call this one-dimensional structure, 1D structure. So Prokudin distribution functions, we say, give us access to the so-called one-dimensional structure of the nucleus. Very important. Okay? So we are actually resolving the particle nature of the quark inside of the proton. Okay? So all this, what I draw here is, of course, is in the mind of a theorist. But it turns out to be a very good approximation what experimentalists measure. Now the question is, now how can we study 3D structure? what is the 3D structure? Okay. So in order to think about 3D structure, let's start thinking about semi-inclusive deep analysis scaffold. Okay. Let me draw this. We have our leptons. They start scattering work. Okay, so the scattering of work can be complicated. So things can go out or in, if you like. So then we have another quark, and then this quark here would produce all these particles. So all these particles here or there, for instance. And what we'll do is that we'll detect one of these particles. We call this particle H or some momentum pH. So this and this are not observed. That's what's experimental view of that. So we are studying the scattering of the lepton plus proton, and it goes into detect this lepton L prime. We detect this particle H, and we don't detect anything else. It's the semi-inclusive analysis scattering. Okay, so let me give you now mathematical variables. So the working variable is already, so it's q squared divided by 2 of q. That's the working variable. It was already here, even for so-called deep analysis scattering. So then nothing final state, but for this lepton. Another variable which is important is y, which is p dot q divided by t dot l. And this variable is called inelasticity. We can trace it back to the energy loss. And the third variable, z, which will be p dot ph divided by p dot q. Okay. This variable is going to be important for cognitive. Can be traced to the fraction of the particle momentum carried by this hadron. Okay, so now let's just think about this for a second. So, momentum of the hadron here, say, is p, then fraction x of it is carried by this. Well, you can call names, a, for instance. Now this interacts with the lepton. Okay, then we have work with P, which will be A plus Q, and then it fragments into the hadron H. I'm not sure which process here is happening. And fraction Z of this momentum is going to be momentum PH. So something important here, because it's for the virtuality of this Q squared is equal to approximately S times X times Y. Okay, so if you haven't derived this relation, Q squared approximately S X Y, do it as a homework. Even if you derived it, try to do it, see how it works. Okay, so S here is the energy of the process, is the energy of this thing. It's L plus E squared. Approximately 2 P dot L, if I neglect also left. Okay, so far so good. So this is, well, it's our experiment list. So now what is happening in the mind of the theorist? But among other things, well, we can do the following. So let me draw this slightly different. Okay, so let me choose now my virtual photon as a direction. So virtual photon goes in some direction. So I will say, okay, virtual photon Q. It interacts with the proton. Here's my Here's my proton, and the quark interacts with it. So now imagine I have some transverse momentum associated with this vector pH. Let me call this transverse momentum PHT. Let me keep this transverse momentum low. Okay? So something like similar to the masses or typical hadronic scale. So what is happening here is that we have a QCD process. Well, we haven't spoken yet about QCD at all, but we know that, of course, quarks and carry colors. Quarks like to emit gluons much more than like emitting the photons because of the coupling constant. Coupling constant for strong interaction is bigger. That's why it's strong interaction after all. So a lot of gluons will be emitted. But imagine now, after all this thing, we get pretty low transverse momentum of the hadron that we measure. So one of the possibilities can be that we have some intrinsic transverse momentum of quark inside of our proton. And let me call the name, it's K proton. Now, after it bounces off our photon here, we can go to a particular frame. So infinite momentum frame, we can choose bright frame. For instance, if the bright frame is such that particles just go in the other direction. Right? So once it's happening, our P will have the same transverse momentum because Q doesn't have transverse momentum, so there is no way for Q to introduce this transverse momentum. Now there will be some non-perturbative process of fragmentation of this quark into observed hadrons. Okay, but what I told you there is that fraction z of this momentum will be carried towards my final hadron, and so this will be z times k curve in terms of the transverse momentum. And then, of course, there are some non-perturbative interactions happening. And therefore, it's not only going to be that, but it's going to be some additional transverse momentum, which we call P curve, which would then produce our hadron momentum pH or PHT. So PHT will be approximately equal to Z K curve plus P curve. Okay. So now, I told you it was one of the possibilities because, of course, gluons can be emitted by the quarks, and in fact, they are going to be emitted. And so, of course, one can imagine, well, why this transverse momentum PHT is small? If I emit one hard gluon, it cannot be small. But if I emit two hard gluons in the opposite directions, it can be small. And therefore, it's not only this picture here that I draw, where I'm saying these are small momenta associated with somehow non-perturbative dynamics of quarks inside of the proton, which matter. It can be also gluon radiation and all sorts. And so for the treatment of gluon radiation, we'll do it actually tomorrow. What I'll stick to today is just imagine that this is what. Imagine that this is the most important. Why it is the most important? Well, if you want to emit two hard gluons, you'll pay a price of alpha squared. For very small transverse momentum for this hadron, one may assume that this non-perturbative momenta are important. Okay, so now let me just pause for a second and tell you now that we wrote this, okay, what are we going to be talking about? Say these things and these things. We'll parameterize our distribution process, we'll parameterize our fragmentation process. So before, once I was drawing this diagram, I said, okay, this was some function f that encodes x. Okay, so now it encodes x, but also it should encode this a curve. Okay, paper, which is a two-dimensional vector. It's a transverse momentum and transverse plane, so it has two coordinates, x and y. It has to be there because otherwise I cannot trace it back to this guy without real recognition. Okay? And the functions that now include both x and transverse momentum, paper, intrinsic transverse momentum, are called transverse momentum dependent distributions, or TMDs. Sure. Okay. Remember, I went to my dentist and I learned that actually TMD was some sort of disease. For dentists, okay, but for a physicist, TMDs are transverse momentum dependent distributions, and they encode x and they encode ktx and kty, and therefore free variables and therefore 3D structures. 3D structure in the momentum space. So this is where they arise. And this is how we can study them. So in order to study them, we would need to detect the hadron in the final states with some particular transverse momentum. Now, why one should be excited about this? So now that I told you what those, say, okay, perfect. We study deep inelastic scattering, we pick up one hadron in the final state, and we concentrate basically on the fact that this transverse momentum is small enough. Why should you be excited? Think about this fact. So this photon here with large virtuality was revealing the nature of the parton as a particle. Okay, in deep inelastic scattering, we basically prove logarithmic scaling. Yeah, that's perfect. So you'll see about this, but working scaling is still there. Therefore, it resolves it as a particle inside of the nucleon. Now, however, this particle is bound inside of the proton. Okay? It's bound by some mysterious process, which we call confinement. We don't know origin, we don't know details of confinement. So everybody wants to resolve QCD. But the question is, what are the handles on the mechanism of confinement? Well, this intrinsic transverse motion, K-perp, if anything, tells us about some details of this confinement process. So if we have some sort of theory that describes confinement, this theory will have to describe how these particles are distributed in terms of this momentum, because they are inside of the proton, they are wiggling there inside, and they are confined. And therefore, by studying those, we get, well, a bonus. What we get is a three-dimensional picture of the nucleon. We can take the tomographic scans, and I'll show some examples of tomographic scans in a little bit. But what's important for me, what makes me excited, is that when I studied this, I studied some imprints of the mechanism of confinement of quarks. Okay, so now factorization is proven in terms of transcendental dependent distributions. So the same here. So we'll define a function, we'll call it D, and it will depend on Z and P perp. So D is the function that describes fragmentation of a quark in the final hadron. Now it's going to be not one-dimensional, but three-dimensional. We'll also have the imprint of confinement in terms of this dependence. Factorization is proven, and it took a lot of time, and actually one of the people who proved the factorization will give the lecture after me. It's proven for CDIS. That's the process that we study. It's the electron ion collider. Okay. So let me just draw its schematic. This is like this. It's proven for Drell-Yan. Drell-Yan is a process we have scattering of two hadrons P1, 2, and we produce lepton pair in the final state. Okay, it's like this, or it's proven, so this is the Drell-Yan, or it's proven for lepton positron annihilation into a pair of hadrons PH1 and PH2 in the opposite hemispheres. Okay. So now what's important is that if you look at these diagrams, you'll see the common, always two hadrons, E and PH, P1 and P2, pH1, pH2. It's sufficiently inclusive, so I get a lot of particles flying here and there that I don't detect. It's one electromagnetic system, which probes it. And the transverse momentum of what we study, so here it's pHT, this will be called QT, will be much, much smaller than Q. Then we want to be sensitive to this intrinsic transverse. So these are underlying properties of factorization. So that's only 15 minutes. Why do we want to study this? Well, experiments, there are many more things to measure, because now we have one more particle in the final state. Theory, we have more vectors to construct distributions. It allows us to study correlations. For instance, correlations between transverse motion and spin. And there should be some imprint, I told you, confinement about that. Okay, so now let's start a little bit talking business. So let me go from this hand waving arguments. So in my lectures, I'll give you a lot of hand waving arguments. I'll give you a lot of mathematical arguments. I'll tell you using the orthogonality of Bessel functions here and there, this and that. So don't be swayed by the mathematical rigor or the absence of mathematical rigor. So it can be good, it can be bad. Okay, so I'll give you an example then mathematical rigor doesn't help, for instance. So let's talk now about this thing. So that's what we are doing. So we have those diagrams. It's P and P. We have this work here, there. Okay. So what it is at all? Okay. So we need to write it down somehow. Well, we'll be using Dirac notations. Of course, we'll say here's our proton, some spin S, and here's our antiquark bar. It lives in the configuration space somewhere. Okay. We leave configuration space when P. Well, this one will be at 0. So it's irrelevant where they are, it's just the distance between them. Some vector D. So get B. And this one will be at 0. Here's our proton again. Here's the P and S. Okay, so it's a Dirac matrix, so we can have Dirac indices here G, I. So this thing will be psi phi of I and G, and this matrix element is what we know as a correlator. Okay, so that's what theorists call a correlator. Now this matrix element has to be projected. We can project this to the unprized quarks. So as far as it is a Dirac matrix, we'll use the basis of Dirac matrices. So we'll use gamma plus. Gamma plus is gamma 0 plus gamma p divided by square root of 2 to project to unprized quarks. We'll use projector gamma plus gamma phi to project on longitudinally polarized quarks. We'll use a projector of I sigma alpha plus gamma phi to project on transversely polarized quarks. There are sigma mu. Sigma mu versus I over 2 gamma mu gamma mu. Okay. This is how it would look like. So how do we perform the projection? What we do is that we call it something like this: psi gamma equal to 1/2 the trace of our correlator phi with particular gamma structure gamma. And then this is what happens. We find out a lot of functions. So this is this famous table of Team Ds, and I think those of you who are in the field, you saw them. So if you think that this looks terrible, think about about this. And then I write it in terms of all these functions, in terms of projections with gamma plus, gamma 5, I sigma alpha plus gamma 5. Okay. So they will look like this. So I'll talk just in a second a little bit more details and actually show how things are done. Let me just give you the names. I think the names are probably easier to give here because they're actually written. So I stole them from our book. Okay. So this one, then we project on the unpolarized quarks. We can have a structure which is called F1, which describes the unpolarized quarks inside of the unpolarized hadron, similar to just Barton distribution functions F1. Now, unpolarized quarks can live inside of the transversely polarized nucleon. Okay? So the spin is a pseudo-vector. We would like to construct here a structure which is a scalar. So we need to multiply this pseudo-vector by another pseudo-vector. Another pseudo-vector can be constructed by this antisymmetric tensor epsilon t rho sigma and the transverse momentum kt rho. Okay, so now this thing will be a scalar, therefore we can assign some other function. And this some other function would be so-called Sievert's function, or wait a second, there, Sievert's function, which describes unpolarized quark inside of transversely polarized hadron. Okay. Turns out that this function is a T-odd. So now QCD is T even, and initially it was thought that due to the symmetries of QCD, this function has to vanish exactly. Okay, so this is mathematical rigor. You look at these things and then you say what those functions are, what symmetries they obey. And turns out that this function is T-odd, and therefore due to symmetries of QCD, it should vanish. It doesn't. Turns out that it was clarified that non-vanishing, then one takes correctly the so-called Wilson line. We haven't spoken about this line yet. We'll talk about this and many more. Okay, so it's like, if you like, it's a zoo, many different things. So there's one expansion for, this is for the longitudinally polarized quarks, and this is for transversely polarized quarks. And there are all these names and all those things here. Okay, and of course, for each one, I can give like 1 hour, or anybody can give 1 hour lecture here. So we'll not do that. We'll probably just look at some particular thing that I need to demonstrate before we adjourn. So I told you that all the measurements are performed by our experimental colleagues. And they performed in the so-called momentum space. They measure moment of particles, moment of particles. Now, then I did this. Well, it was a little bit hand waving, but I introduced this variable B, and I said this is configuration space. It's not experimentally measurable space, but this is what happens in the mind of the theorist. And this configuration space is Fourier conjugate to our experimentally observed space. Okay? And therefore, we can write our decomposition of whatever we study in momentum space. That's where we measure things. Why am I going to which is here? You see, I'm using all these vectors, AT here, ST, and so on and so forth. Or we can write it in configuration space. BT, ST, and so on and so forth. Okay. So now, the first thing that I wanted to give to our theorists is actually, I'll teach you how this happens. So what are we going to do? We'll go from this KT space to the transfer space D and back. Okay? Let me just say that this is KT and T. Okay? And we will actually derive this formula. Okay, so this is where I think I'll end the lecture today. As we started a little bit later, I'll probably use 5 minutes of your time. So how the Fourier transform is happening? Fourier transform is important in classical mechanics. It's very important in quantum mechanics for obvious reasons. So let us define the Fourier transform of the function in the configuration space. And what I'm interested in this particular part of this vector which will be Fourier conjugate to my transverse momentum. Okay, so that's what I want to study. So I'll be defining my two-dimensional Fourier transform, and this will be the integral of T2 kt of, well, usual minus I dt dot kt of my function in momentum. This looks like this. Okay, so a warm up for us to do this. Let's write what this thing is. Let's take d2 kt from 0 to infinity. Integrate also the angle phi from 0 to pi. Okay, what we integrate here is minus I dt kt absolute value times the cosine of the angle between them. Let's call it phi, f of kt. So the angular integration now can be performed because nothing depends on the angle but this exponent here. And then this thing here is nothing else as 2 pi times the Bessel function kt. Bessel function first kind, J0. Okay, so after all this, come to the conclusion that this thing is equal to 2 pi integral of dkt kt J0 of dt kt and the function in the momentum space. Okay, so now I'll not derive it, but easily demonstrate. And if you haven't done it, please do it as an exercise. So the inverse of this will be 1 over 2 pi integral of d dt dt J0 of dt kt f tilde of dt, Fourier conjugate of my function here. Okay, so in order to demonstrate this, you'll have to use the orthogonality of Bessel functions. Okay, I told you that I'm using this towards mathematics. Okay. So now, of course, we want to perform the Fourier transformation of the formula that was before this, the first line. So what I did in 2011 is that I introduced a particular derivative of the Fourier transformation. And then each time I talk about those derivatives, people ask me, but what these things are. Okay? And that's why I want to teach you, so that at least from you, I will not have those questions. So what I introduced was this transverse derivative with this index n here. By definition, just n factorial of minus 1 over m squared dt, partial derivative with respect to dt, to the power n, f of bt, the same f of bt that you saw just a second. So this derivative hits this thing, and one can demonstrate, let's do it, that's equal to 2 pi n factorial m squared to the power n integral of kt dkt kt divided by dt to the power n gn now of dt kt of f of kt. Okay, so this is how this Fourier transform works. So it's in particular derivative. So now if you look at this derivative, pt has dimensions of gv minus 1. M squared here is important in order to make this dimensionless. It's good. We like dimension things. And now we have all this beast here. Okay. And then people see this, they ask me all the time, like, my gosh, what is that? So let's perhaps dissect what is happening here. We'll try to find limit of dt goes to 0 of this thing, f tilde n of bt. Okay. So now, when we take this limit, we have to take the limit of our function gn, and the limit of gn, those of you who are theorists, they know very well. It is 1 over gamma m plus 1, the power z over 2 the power m. Okay? Now these are numbers for me, okay? So it's not a bar that I'm trying to derive. Okay? I'm sorry if you cannot see it, it's already on the web, okay? So we can just solve. Okay? So this one will be just m factorial for me. That's how this m factorial arises. So if I take this bt goes to z limit, my n factorial will cancel with this n factorial, okay? And then this z over bt after the some algebra will get 2 pi the integral kt tkt kt squared divided by 2m squared power n f of kt. Okay, so that's an easier formula. Okay, so maybe it's still gibberish to you, but this was introduced around 25 years ago, probably more, in 90s. Oh my gosh, many years ago, 30 years ago, by people who started studying transcendental dependence, factorization, and formalism. Okay, those are called moments of TIMDs. Okay, so they can be, these moments of TIMDs can be traced to, for instance, what is the average width of TIMD distributions? What is the average shift of some particular TIMD distribution, depending on what this power here is? And now the Fourier transform of those moments is just this thing that we introduced in 2011. So it looks very complicated, but in fact it's not very complicated. Okay, so now let me just use this and show how the Fourier transform of our distributions happen. So then we decompose, say, f of gamma in terms of functions, so on and so forth. You will see that in this composition, we have something like kt I times atj, where I and j are just indices 1 or 2. So those are two-dimensional derivatives. So we need to Fourier transform kti times ktj of f of at. So now, how we do it? In order to pull kti or ktj, we need to take the derivative in terms of dt, because in our Fourier transform, we always have, well, it's not written here, but we have this exponent of minus I kt bt. And therefore, what we do is that we say, okay, we need to do this transformation. d2kt, ati, ktj of f of at, and then we write e to the minus I kt dot bt. Okay, so these things can be transformed into derivatives onto this exponential. And one can show that it is actually plus I eti over bt partial derivative with respect to bt. I etj over bt d over bt. And this thing should hit our Fourier transform now, because now we have pulled everything out. Just the Fourier transform, which we wrote in the first part, which is dkt at j0 kt dt of f dt. Okay. So welcome to my life. And you do phenomenology, you do a lot of Fourier types. Okay, so now kts are pulled out of the integral. They are derivatives. They look like this. And so I'll give you just one example. So I want to explicitly derive this term. So let's just use one example. That will finish the first lecture. First example will be this. So that's the integral of v t d2 kt of ati of e to the minus et kt of f of at. Okay? We want to Fourier transform it. We know now how we do it. We just apply this operator here. That's the derivative to our J0. So now let me use the trick here. Okay, so the magic of the eraser. So we have just one of these derivatives sitting here. So it's I, bti over bt, e over v bt. Hitting this. Okay. So in this formula here, it's only Bessel function, it depends on bt. We take the first derivative of J0, we get minus J1. Okay. We have, of course, to take the derivative of this, so we'll get 1 kt out of it. Okay. So we'll have this. We'll have I bti over bt 2 pi integral kt kt minus J1 kt multiplied by kt because we also hit the kt times bt times function f of kt. Okay. Now let's take this minus out, do the transformation, and we have minus I bt I 2 pi integral kt dkt kt divided by bt. This was our bt here in the denominator. Okay. Of J1 kt bt times f of kt. Okay. And so now, if you're paying attention, and of course I erase this. This whole thing is one of the examples of these derivatives which we introduced in 2011. So they correspond to these functions which we call f tilde of some. So let me go logically here and say that this is equal to minus I dti m squared. Well, remember there was an m squared because I wanted my derivatives to not have dimensions, but now m squared has to be here because there was no m squared floating here. And I'll have f tilde 1 of bt. Okay. And therefore, now that we have this, now that I have this rule, then I write phi of gamma plus, which is equal to f1 of x at minus epsilon ij ati stj divided by m f1t perp of x and kt. I'll Fourier transform this, and I'll write that this one is Fourier transformed now for later in B space. The mind of the theorist would be equal to f1 Fourier transformed of x and bt now, and I can even add 0 here, meaning that there's no derivatives that hidden. But now I'll plug this one in here instead of this kt. Now I have plus I epsilon ij bti stj m f1t perp 1 of x bt. This is how this Fourier transforms are performed. Okay, so now homework for you: perform other cases and do it slowly and check what is happening. So you'll be able to actually transform all those functions. Yes, all these ingredients here. Okay, so now those of you who know who study phenomenology or experimental theory know how to perform Fourier transforms of our correlators in terms of the underlying functions from kt space to bt space. Bt space will be important because our next lecture, what we're going to be doing, will be actually solving evolution equations Evolution equations are written in BT space. In the seminal papers by George Thurman, John Collins, and Dave Sofer. Okay, so now, however, before we adjourn, let me have just 5 minutes of your time, because as I am a criminologist, what I like numbers. And more than numbers, I like actually computers codes. Okay, so let me go here. So you have an example of a code which you can run on Google Cloud. So on any computer it should work. It should work even on your phone. So this code here is a library which we created for our results of extractions of all these transcendental dependent distributions that we performed in 2020, 2021. So you see the authors, many people from different laboratories and universities: Penn State, Temple, Jefferson Lab, UCLA, Old Dominion, William and Mary. We were supported by NSF and Department of Energy. So now what this thing is doing, it contains information about two analyses that we did in 2020, 2021. And what I'm doing here is that first line of this code here is just cloning the appropriate GitHub repositories that everything is located. Then I'm using this GitHub repositories and entering one of them. So now here I'm loading our TMD class with some particular extraction that we did in 2022. That's DAC jump 3D 2022. It's like this. And you can do some simple tests. So for instance, well, here I will define the masses, the hadron and the pion. And here I'll evaluate one of the TMD functions. Well, in this particular case, I'll just call it the function which is called transversity. We will not be talking a lot about this function, but if you like, we can talk in 2 hours here. What this cell is doing, it's evaluating the structure functions, because once you measure things experimentally, you measure cross sections. Now we haven't yet spoken about the structure functions. I'll do it at the very beginning of our next lecture. Structure functions allow us to decompose all the cross section in terms of the angular modulations or modulations with respect to vectors such as transverse spin or longitudinal spin. Okay, and so this one would allow you to do this. It would evaluate structure functions for unpolarized case or for case of transverse polarization that has a particular modulation related to the series function. Now here you can load all the data that we have for some particular experiment. I just chose the Hermes experiment. And here what we'll do is that we'll just define the calculation. And here what we'll do is that we'll plot the data with respect to our calculations. Okay, so it's done all on the fly for you. You can try, for instance, get the functions, and this is done here. And we have many more replicas, I think around 600, but here I'll just do 50 replicas in order to show what kind of errors we have on those functions. Okay, and then we'll plot here. Okay, so what we are plotting here actually corresponds to the first moment of the series function, very much related to what we were deriving there on the board as the Fourier transform of distributions from the momentum space to the position space. Okay, so we know them as a function of x. So now this thing here, okay, you see it has only one variable x. Why it has only one variable x? Because the derivative that I showed there that we introduced into 2011 corresponds to a particular derivative of the Fourier transform in B space. It corresponds to the integral of the transmomentum the moments. So now we don't have transfer momentum dependence. We have the total integral here, and that's why one is sitting there. This total integral comes with a prefactor, which is kt squared divided by 2m squared. And that's why then I was deriving in 2011 the Fourier transform. This notation came around the Fourier transforms f tilde of 1, because then you know that we are talking exactly about these functions here. And so here, just for you, say for up quark, we know this is a negative function. For down quark, it's a positive function. Okay. Before we finish, I was talking about those, and of course, I didn't try to steal everything from George's lecture, but the probabilistic interpretations functions that we extract, in particular PDFs. At the lowest order, we have probabilistic interpretation. It's a probability to find something. So now I have something here which is negative. What's your interpretation of that? I have extracted something, well, which I care about. I told you these things have imprint of confinement, all these big words and all that. Okay. I did tell you that in order to go from what our experimental colleagues do to what happens in our minds or theories, we have to do certain operations. And at some points, we are in our worlds, PTs, and then bam. If something is negative, if it's not a big surprise to you, it's a big surprise to me, because I was expecting squares to be always positive. I was talking about probabilities and imaginary parts and that. Any simple idea why this function at all, anything can be negative?
It's soft shell.
I haven't even started drawing the diagram. I had it, if you open my lectures, I was very ambitious. I was going to show how Eichmann propagators happen, so that the gluon radiation and that. Everything that I did so far had no QCD, because QCD is the first lecture of George. He hasn't started yet. Everything I did was Parton model. Very old-fashioned Parton model. Why do you think his name? And you're asking yourself, I even don't know what this thing is. He didn't tell me, but it doesn't matter. I extracted something from this, and I was talking about this Parton model, about probabilities and all that. I get this negativity. It has nothing to do with gluons yet. They are short. Particles are short. One of the things that we'll discuss tonight is, can we actually motivate our Parton model? Why? Then I drew this diagram. I was drawing this diagram as if these were very tiny balls flying around. And then I was drawing this diagram. I was actually thinking everything is on mass shell. So can we motivate this? We'll be talking about this tonight. I know for a fact there are a few experts in Team Ds in this very room. You want not? Can you tell them? Yes. I don't want to put you on the spot. Anna, we can do it. The answer is very simple, actually. I mean, I'm not trying to be very scientific here.
Right. Part of the reason that things can get negative is also because of renormalization general. That's if you have different scales.
It's not here. It's not that reason, because that is too much negative. So a little bit of negativity due to renormalization, then we grump it. So it's 4 square. If I do q square equal to 50, it still will be negative. But renormalization, as you say rightfully, can lead to even Parton distributions be negative. I get it completely. At lower scales. At higher scales, they have to be positive because they correspond to. Yep.
This from Joyen process.
Oh, you know about the sign change. You know about the sign change of service functions.
Because the join process involves multiplication.
All my lectures are self-contained. If I haven't told you about the sign change, it doesn't have to matter. I don't anticipate anything. All my lectures, all my questions are based only solely of information that I gave you so far. Well, this is the function which corresponds to Jelian. In series table, flip the sign. We'll talk about this tomorrow, okay? It's not about this. I'm eating too much of your time. The simple answer can be a probability. Probabilities are positive. What's the probability of its raining? Minus 50%. Cannot be minus 50% of probability. It cannot be a probability. This is one of the examples of the functions that don't describe probability. Those are correlations. In this particular case, if we still have it on the blackboard, yeah, we do have. You see, it's BT times ST. Okay? It's a correlation of partonic motion and transverse spin of the nucleon. That's the beauty of it. Unlike Hartman distribution functions, some of TMDs have nothing to do with probabilities. They can be negative. This negative correlation may indicate, if one stretches, this Parton model dynamics, some particular interpretation of the correlation between the orbital momentum created by quarks and the transverse spin of the nucleon. And in particular, one can say if there's contribution of, say, from up quark on down quark, positive or negative, to the nucleon spin itself. So one of the things why I think we should be excited about 3D structure is that it's not just about probabilities. It's also about correlations. And it is about the imprints of the confinement. And that's why, to me, it's very interesting to study TMDs. With that, let me finish the first lecture. Any questions? Go ahead. Go ahead.
Making a divergence, like keeping the size hyper near to each other, right?
Yeah, one has to be careful to do this limit. And one has to do it, one can do it systematically. So what he's anticipating, he's saying, we have two different worlds, like DGLAP world, where we neglected all KTs. We have this transmomentum dependent distributions, which have transmomenta in play. Once you have transmomenta in play, you have different evolution equations. They actually have very different origin, very different origins. So then we take this limit, BT goes to 0. It's the same if you just write your Fourier transformation and take this limit. You'll figure out that your exponent goes to 1, okay? And then what you have is the integral of the whole transverse momentum from 0 to infinity, okay? So now George has proven that this type of factorization works for the momenta which are small. For large momenta, we cannot really talk about TMD factorization. And the question is, you're integrating over the whole region, or the whole region. Even in the region where your TMD factorization is not applicable, and that what you get as an answer, of course, divergences, very different divergences on the right and left-hand side. One is UV, the other will be UV divergence and repeat divergence. Then you integrate over repeat divergence, who knows what you get. Be assured, it is a magic. Well, it's not a magic, but it's a beautiful, actually, one can have a very beautiful proof that they work perfectly. Okay? It's not only me who did it, but also Tommaso, for instance. You integrate this thing over KT, and in spite of all these differences, you get exactly the same answers to the picture which is described by 1D distributions and 3D distributions. It's just mathematically, to me, it's a masterpiece how it works. But it does, okay? But somebody else asking. Was it the same question?
I have another question about it. Like, so you never have an isolated upwork, right? So these
Distributions are always contributing to a probability in the sense that you're always summing over all the forks, so all the TMDs for each fork. So couldn't the answer just be that, yeah, the contribution from the up quark is negative, but overall it's never negative?
So here how it happens. Once we have scattering, we cannot have, well, I think there are ideas, especially in jet physics. Jets, for instance, figure out what was originating, like up quark or down quark, looking at the particles, how they distributed, what the charges and so forth. But if you do semi-inclusive classic scattering, we always have the sum of charges squared times the contributions of that. Okay? And what happens, one needs to have enough observables in order to be able actually to distinguish between contributions of up quarks and down quarks. So in order to have enough observables, one needs to have different targets. So we have data from proton target, deuterium target, and neutron target, helium-free, which is effectively polarized neutron. And we have production of particles, which is pi plus, pi minus, for instance, and pi zeros. So there are enough observables actually to disentangle them. So what we see here is actually unambiguous. So it is negative. But even before we started it, we knew that large NC was predicting it would be negative on approximation equal to each other, first of all. And secondly, we knew it was not probability, it was interference. That's why. But very, very good question. You need to have enough observables in order to actually tag on extract information about various quarks. Let's have maybe like a 10-minute break and we'll continue so that we don't go too much beyond the program schedule. All right. Thank you.
Yeah, we'll gather again at 11 and George Sturman will give the next lecture. With the USBs, if they copied successfully, pass them on to a friend. If you have trouble, let me know. So enjoy the